Alright, in today's video we're going to be talking about parameters, and in particular I'm going to be introducing EBP, or the extended base pointer, as another method in which we can use to access parameters that are, or the values that are passed to a function when it's called. So as a review, what happens when a function is called? Well, we have the call instruction, and what the call instruction does is it pushes the next address, so the address that that function should return to, onto the stack, and then it moves the address of the function into EIP, so that execution, the instruction pointer, will begin executing instructions at the location that is that function. When a function is done executing them, we need to return, and what return will do, that instruction, it will pop whatever is currently on top of the stack, which should be a return address. That's why we have to be careful as we're modifying the stack in our functions. So it should pop that value, move that into EIP, and that's how the program knows what location to go to, where to return once a function is done. So what about parameters? Well, so far we've been looking at this, what I'll call method 1, and that we have parameters, they're above the return address for a function, and we can reference those parameters using ESP, or the extended stack pointer. Remember that when we're in a function, we want to reference those arguments. ESP is pointing at the return address. So if we need to reference a parameter, the first one that's going to be available is going to be at ESP plus 4, and the second one ESP plus 8, and the third one ESP plus 12, or C in hex. And then you'll continue to count up in increments of 4 bytes, because we push 4 bytes at a time onto the stack on a 32-bit system in order to determine those arguments. So however many that particular function has. Here you can see an example. So we have a program here, and it's going to read from, it's a partial program. You'll see that this code is uploaded video, I think this is 24. It'll be uploaded though and added to our code repository for the class. And so you'll see that I'm going to call scanf. So I'm going to push on the locations, the memory addresses for 3 variables that I've defined, and then the format specifier for that scanf call. Call scanf and then adjust the stack pointer. The next thing is the function itself, and this is what we're going to spend a little bit of time looking at. So once I've stored values that the user typed in into those variables, and I called those A, B, and C, I'll push those values on and then call function 1. Inside of function 1, you can see that I'm referencing those values using ESP plus and then an offset. So I move all 3 of those values into a register, ECX, EBX, EAX, and I start. You can see that the last thing I pushed, that's going to be the closest thing to the top of our stack, which is A, this is B, and this is C. And so I use the registers EAX, EBX, and ECX in order to reference that. So if I wanted to get the value that was at C, that would be the thing that was lowest on the stack. So ESP plus C hex. EBX, ESP plus 8, and then move into EAX, ESP plus 4. So this would be the value of B, and then this would be the value of 4. Once I move those into registers, I can add, so add to EAX, ECX, add to EAX, EBX, and now I can return. And since this function is returning a value, I left the value in EAX, and you can see that once this function returns, we return to this next instruction. It cleans up the stack pointer, cleans up the stack. So we pushed 4, 8, 12. We add to ESP 12, or C in hex. Okay, now we clean up the stack. We can move on, and I use a printf to print that off. So push the value that's in EAX, that's the value that was returned by my function. Push the format specifier for a printf, call printf, clean up the stack, and now we're done. And if we ran this program, you would see that it would prompt via the scanf to input 3 values. It would push those or call this function, which would add them together, and then it would just print off that result. Okay, I'm going to step through that using GDB. So I'm trying to use GDB throughout the course here so that you can just hopefully build some familiarization and seeing it being used a few times at least anyway. So I'll exit that slideshow. Here is our program. Okay, it's a little bit more because we're going to go through some more examples today. So you can see though that function 1, we'll talk about function 2 shortly, but function 1 is all that we're going to be referencing here. So we're going to run it, and we're largely going to ignore what happens at this point on. Okay, so I've already got that built. So video24.out is my executable program, and we just do GDB and then the name of the program that we want to run. And once we do that, we should see it load up. At this point, I need to define a breakpoint. I need to tell the program, or tell GDB, our debugger, where to stop. So we can say B, or you can say break, whichever one you prefer. If it helps to spell it out, just to help remember what the command is, then you can do that. But B for break, and I'll do ASM main. Okay, so it says set a breakpoint at that memory address, which happens to be where our ASM main function is located. Now we can do R, and that'll run the program. And you'll see that the program will run until it breaks. And if we do a disassemble, thought I had do not disturb on, sorry about that. Okay, we'll see that it more or less looks like what we'd expected. More or less looks like our original program, except that here you can see these pushes, C, B, and A, before and scan format, before our call to scanf. Right? We're actually pushing memory addresses because that's what scanf needs. It needs a memory address to know where to store the values that the user types in. So that's some of the differences you'll see as you start running a debugger. It's because now that the program is being executed, we know what these addresses are. So those are the values that are in fact being pushed before this call. You'll see a call to this address, and typically GDB will put to the side what that is. So we can see that's a call to scanf, here's our call to fun1, here's a call to printf, here's a call to function2, and then here's a final call to printf. Okay, so don't forget you have, and here's a little cheat sheet, we have the ability to single step, stepping in and stepping over, and we went over that in a previous lecture. So if you don't remember, I don't remember which one it was offhand, but you'll need to refer to that, or send me an email. I'll be more than happy to walk you through it again. Let's say at this point though, I just want to jump right to this call to function1 or fun1. So I'm going to go ahead, I'm going to set another breakpoint. We can see that we're going to push the value at these locations. So that's what this is showing us right now. We're pushing the value that's at this location, and this location, and then we're going to call the function. Okay, and that's what we're doing right here. We're pushing those values. We're saying dereference whatever's at that location, and then making sure that we push a D word, because that's how much data we stored. I declared these up above, A, B, and C, as D words. Okay. So pushing those three values on before we call function1. So I can set a breakpoint down here on that function, on that location, B at fun1, function1. Okay, now if I type in C, that'll continue execution. You'll notice that the program, because my function is called after scanf, so now it's waiting for me to type in some values. So I'll put in 1, 2, 3. Okay, and now it hit my second breakpoint, which is at function1. So if I do a disassemble, you can see that we're inside the function. We move into ECX, ESP plus C, move into EBX, ESP plus 8, move into EAX, ESP plus 4, add, and then return, which is this function right here. Okay, you can use this command, and we've used it in the past, x/ and then the number, and this will give us, will print off memory, the values in the memory locations. This will print off 4 locations, and we can reference from ESP. And let's do this. Okay, so that trailing X changes the format. You see, before I didn't have that, and it printed off just the numeric values, or the base 10 it looks like. The X does hexadecimal. So we can see now that we have a hexadecimal value for the address, hexadecimal values for 1, 2, and 3. It's a little bit bigger. Okay, remember ESP. ESP is the top of our stack. What did we do last thing that we did before we entered this function? We had a call instruction that pushed the return address on. Right? This is the next instruction that we're going to execute. This is where we're going to return to. So ESP, this is the top of our stack. Right? That's the return address. This is the next thing on our stack. Then the next, then the next. So this is ESP, this is ESP plus 4, this is ESP plus 8, and this is ESP plus 12, or C in hex. Okay, so I just wanted to show, based off of the value of ESP, that this is in fact what our stack looks like. Okay, from there you can go ahead, you can type in C, and that'll continue. And since there are no more breakpoints set, then it just prints off the result. So the printf, it calls function 2, calls the printf, and we'll go through that here in a moment. All right, then quit to quit. Now we're back to our terminal. All right, so what about EBP? So we have the extended base pointer, and what this is used for is it's used to point to the base of a function. We're going to reference those arguments based off of EBP so that anytime we modify the stack inside the function, EBP doesn't change. It's the base of that. It's the base pointer. It's the base of a function. And so we're going to go through 3 examples here in order to help illustrate that. So the benefit is that whenever we modify ESP, whenever we modify the stack in the function, we don't have to worry about that. Arguments will always be essentially statically allocated based off of the value of EBP. So what does that mean? Well, we're going to do 2 things that we enter a function called the function prologue and the function epilogue. So at the beginning of the function, we're going to push the old value of EBP because we're going to use EBP, so we need to save it. We've been talking about saving registers that we use in our function, and that's the same concept applies here. We're about to change the value, so we need to save it so that when we're done, we can restore it. Okay, so once we do that, let me switch to pen here. Okay, so here's our prologue. So once we save it, then we're going to move the value of ESP into EBP. And this will be the first thing that we do inside of a function. So we're saving currently the top of the stack, which is the value of ESP. We're moving it into EBP. And now if anywhere else in the function we do any other pushes, we modify ESP, we've established our base. Because EBP, at the time we've entered this function, is now saved with that, which was currently the top of the stack at that particular moment in time. Okay, we'll do things inside the function, and then we'll have the epilogue. Once we get to the epilogue, that means that about the only thing that we're missing here is our return. Okay, so we're done with our function. We're getting ready to return. You'll typically see these last 3 instructions. This is the epilogue, and that we move into ESP, EBP. What was EBP? Well, at the time we entered the function, right, it was the top of the stack. When we enter a function, what is ESP pointing to? Well, it was pointing to, I'm sorry, it wasn't, because we pushed EBP. So by the time we enter the stack, we'll have, arguments here. We'll have the call instruction, so we'll have our return address, and then we'll push EBP. So now we're going to have the old value of EBP. So this is where ESP points to. So by the time the prologue is done, this is what ESP is pointing to, is the old value of EBP. So what does the epilogue do? Well, it moves EBP into ESP. So if ESP is changed throughout the execution of the function, this resets it so that it points back to here, which is old EBP. We pop EBP. So now we're restoring the old value of EBP because we're pointing right here. So we restore the old value of EBP by popping that, whatever's currently on the top of the stack, which should be the old EBP value, into EBP. Popping will change where our stack pointer is pointing. And now, because that should be the return address, we're returning. The ret instruction will pop that address off, that value off, move it into EIP. Okay, it gets a little bit, I don't know if confusing is the right word, but it can be a little bit much to keep up with it. So, if after today's examples you're still not quite sure exactly what's going on, use a debugger, use the dump regs command, draw some diagrams, and just trace through it to the point where you feel comfortable in understanding what's happening here. Okay, so this is more or less an example of what we just talked through. Get my pen back. Okay, not sure what just happened. Try that again. All right, so let's just say that we have, this is part of a program. We're getting ready to call function 1. So we push 3, push 2, push 1. Right, so we're seeing those values being pushed on the stack. So ESP, as we push, we have our stack pointer, and it went from here to here to here. Okay, now we call function 1, so that pushes return address on. So now ESP is pointing here. Once we push that value on, we go to and start executing instructions for that function. So you can see that now we have the prologue and our epilogue. Okay, so now we push EBP. So now we push the old value of EBP on right here. So now ESP is pointing to this location. And we move ESP into EBP. So as far as our base pointer goes, EBP is now pointing here as well. Right? That's what essentially establishes the anchor, because, or the base pointer, because whatever happens now inside of this function, right, we push, we pop, it doesn't really matter. ESP is going to be what moves. Also, the next thing that we do is we push ESP, push a new value on here. Right? ESP is going to point to that new location, but EBP is not. EBP is staying right here. And so that allows us, instead of referencing arguments based off of ESP, which is always going to, which can change, if we reference them off of EBP, they're always going to be at the same offset from EBP. Okay, and we got a couple more examples, so we're going to continue to kind of build upon this idea. Okay, last thing that we do then, the epilogue, is we move EBP into ESP. Right? Well, at this point in time now, we don't really have to care where ESP is pointing. It could still be pointing right here, where it originally started. It could be somewhere else in the stack. We don't really have to care, because we're moving into ESP the value of EBP. Where does EBP point? Well, it points right here, which is the old value of EBP. Right? This is the place that ESP was pointing once we finished executing the prologue. So we move that into ESP. We now pop EBP. So we pop this value right here into EBP, which takes our ESP now and moves it to the return address, and now we return, which pops this return address off of the stack, moves that into EIP, and our function, our program, continues to execute at that location that it should have returned to. All right, so hopefully this isn't too much of an overkill here, but I wanted to go through this program as an example. So we're just going to focus on this portion right here. I got to put this into pen mode. Okay, so we're going to focus on this portion right here. Okay, so here is our stack. And I'm not going to do the ESP, EBP arrows, because I'm afraid that might be more clutter and confusion than anything. I don't know. So we're going to push the value of C. So let's just say that we entered in 1, 2, 3. So we'll push 3, then we'll push 2, and then we'll push 1. Okay, so that takes care of these 3 instructions right here. Now we call, so that's going to push on the return address, which will be the next instruction, which is our add ESP 0C hex. Okay. Once we do that, execution goes to the function itself. So we're right here. Okay. We're not, at this point in time, we're not dealing with ESP. So this is an example using what I described as method 1 today. So by the time we're in the function, this is what ESP is pointing to. Okay, so if I want to get those arguments, then I need to be ESP plus that offset. So this is ESP, this is ESP plus 4, this is ESP plus 8, and this is plus C. And all these are in hex. Of course, those two don't really matter. Right, and that's why we're doing that offset. That's allowing us to reference those arguments, those values for those arguments based off of the stack pointer. Okay, we do the add, then we do the return. If anything modified the stack pointer in here, then it would modify the offset that we have to calculate in order to reference those values, right? If we had, let's say that because we're using ECX and EBX, let's say that we had in here push ECX, right? Well, now we'd have the value of ECX. ESP wouldn't point there, it would point here. So now this would be +4, this would be +8, this would be plus C, and this would be +10 hex, right? So all of our offsets would change based off of where ESP is. Okay, now here's an example that uses the base pointer. So you're going to see that with this example and the next one, we're going to have our prologue, which is right here and right here. Okay, so we're setting up the call the same. We're pushing values on to call function, I called it function 2. So we can, let's say that we pushed on a value of 3, then 2, then 1. Those are the values of A, B, and C. Now we call the function, so we're going to push on our return address. Call that return address. Okay, and now we're going to start executing instructions here. Okay, this is where things get different, because the first thing that we're going to do in this function is push EBP. So here's our old value of EBP, and now we move into ESP EBP. Okay, so if keeping track of that register, we pushed the old value, and now we moved. So after that instruction, ESP is pointing here. Well, now we move that value into EBP as well. So now EBP is pointing at this location, because ESP is just the address. The location in that register, the data in that register is just the address on the stack. Okay, so now we can get access to those arguments. But instead of using ESP to get their location and subsequently their value, I'm using EBP. So EBP is pointing right here. So we have EBP, EBP +4, EBP +8, plus C +10. Right? We're always going to, when we have this prologue, we're always going to have the old EBP and the return address. So that first argument will always be at the offset +8, and then if there's more, +C, +10, +14, and so forth. Okay? And that works out well, because now EBP is here, ESP is here as well, because in this function we don't do anything different. I don't modify the stack in any of the intervening code between the prologue and the epilogue. So with this one, it's a little less apparent the benefit. In the next example, they'll hopefully make that plenty clear. Okay, so now we can use EBP to reference those arguments. Right? We're just calculating the offset from the stack. Okay, add them up, leave them in EAX, and then execute the prologue, or I'm sorry, the epilogue. So we move into EBP, move into ESP, the value of EBP, right? So that will set ESP to point here, regardless of where it was set. We pop EBP, so that takes our stack pointer now, and it's pointing to this location. And we return, which now pops that return address off the top of the stack, moves that into EIP, and our function returns to the appropriate location. Okay, so this example hopefully will highlight what happens and why EBP becomes important because of the fact that I'm modifying the stack inside of the function. You'll see that we're going to have a couple of pushes here. So I've mentioned now in the past video or two that you may need to save registers inside of the function. So in this function I'm using ECX, EBX, and EAX. So EAX we're going to return the value in, so I don't have to worry about saving that. But with ECX and EBX, maybe I should save those. Okay, so after the prologue executes, I'm going to push ECX and EBX onto the stack. So you can see, as previous, push some values on. Okay, so this is a function that accepts 3 arguments. We have the call to function 2, so this will be our return address. Okay, and now we get to execution right here. So we're going to push on old EBP, and we're going to move ESP into EBP. Okay, so EBP is pointing here, And right now, ESP is pointing here as well. Okay, once the prologue is done. Next thing that I do though is I push ECX. So we're going to push on the value of ECX because I want to save it. So I'm going to restore that when this function is done. And I push on the value of EBX. So after those two pushes, ESP is now pointing here. So if I was referencing those arguments off of ESP, I'd have to change the offset that I was using. Okay, but because EBP is pointing right here, it's the same. Okay, EBP, this is +4, this is +8, this is +C, and this is +10. Right, ESP is now +4, +8, +C, +10 in order to get to the first argument, right, because I modified the stack. So now, inside of my function, this code right here is exactly the same as it was in the last. Even though I modified the stack inside of this function with these pushes, and later on with these pops, this is exactly the same. So I can reference those arguments, move them into registers, do some addition, restore the previous value of EBX, ECX, and then perform the epilogue. So these pops, we're popping or restoring those values. By the time we execute this epilogue, in this example, ESP will be pointing back here, right? We pushed, and then we'll pop, and then we'll execute the epilogue. So we'll move ESP, EBP into ESP, which brings us back to here. We'll pop that into EBP, so EBP won't be pointing there, it'll be pointing to its previous location, and ESP will go here, and then we'll return. Alright, so that's pretty much it. I have the code, but we've traced through the code, and I'm hoping that the diagram does a better explanation than trying to trace through it here, watching it execute and just talking through the different instructions. So there's nothing different here as far as what you're looking at from the examples in the slides. Here's our function 1. Function 1 is not using EBP, it's just using ESP. Function 2, though, is using EBP. So you can see that here is a version, so this is like the second example, we don't modify the stack inside the function. So call that, run that program. Okay, so we'll just do 1, 2, 3, the result is 6, the result is 6. So after each one of those functions, function 1 and function 2 is called, I print the results. And I just use this format specifier here, %d. So I'm just printing the value that was returned from that function. Okay, if I modify, so let's say that in function 2, I push EBX and I push ECX. Okay, I want to save those registers. Now before I return, I pop in the reverse order. So we pop ECX, pop EBX, and save. You'll see that even though I modified the stack, I don't have to change any of this code because we established our base pointer right here. So now I can run that program, 1, 2, 3, and we get the same results. Right, so that's probably one of the biggest benefits of using that. Okay, that's all I have. Let me know if you have any questions. Otherwise, I will talk to you guys in the next video. Thanks.